Okay, so today we're going to work on inverse trig. Basically, depending on where you took Calculus 1, you may have already taken this in Calculus 1, or this might be the first time you're seeing some of this in Calculus 2, just depending on what class you're taking. So I'm going to kind of just teach a little bit of an intro into what inverse trig is. Remember trigonometry, when you say the sine of, theta is equal to, y over the hypotenuse, or y over r, or however you were taught it, or SOHCAHTOA, opposite over hypotenuse. Basically, you're finding a ratio in this relationship for all triangles that have that angle. So what inverse trig does is it basically says what angle would have made that relationship. So remember, when you're dealing with sine, cosine, and tangent, normally you're plugging an angle in and you're getting the ratio. And when you're going the opposite way, you're getting back the angle. So I'm just going to do a little brief intro. You guys should have all seen this in your pre-calc class at some point. So I'm just going to kind of show you where it came from, and then we'll move on to some calculus with it. So basically for us, I drew right in front of us, I drew y equals sine of x, what you see there in blue. I just drew a little, brief sketch or quick sketch of sine y equals sine x. And we want to know what the inverse of y equals sine x would look like. So we want to know y equals arc sine or sine inverse. It just depends on how you were taught. Which technique you use. You could have also called it just as easily. You could call it this sine inverse of x. Those are both the same thing. It's just a different notation. Whichever one you guys are more comfortable with works. Just keep in mind you have to know both, because sometimes they ask you in terms of arc sine and sometimes they ask you in terms of inverse sine, but they mean the same thing. Okay. So basically, the thing about inverse functions is you guys were taught that the only way that you can have an inverse function is if the function that it came from was one-to-one. So basically you have two tests. You have the vertical line test and you have the horizontal line test. So you have the horizontal line test. That tests if something is a function. So yes, we see that the sine graph is a function because I can graph the vertical line test anywhere. But you also then learned that if you want to find out if something is one-to-one, meaning that for every input you have exactly one output, that would be the horizontal line test, right? So if I draw the horizontal line, this definitely fails the horizontal line test. So what I need to do is I need to say, well, why does it fail the horizontal line test, or how could I maybe fix it? So it fails because, in pretty much anywhere I draw, besides at one, I'm going to touch the graph more than once, and this graph goes on forever, so it's going to always be failing. So what mathematicians decided to do along the line somewhere is they said, let's just focus in on one particular part of the graph. So let's focus in on that because it has such a cyclic nature. If we can just focus in on just this chunk, let's say just this chunk right here. So just that little curve right there. So it's not actually a straight line. The way I drew it kind of makes it look like that. So if we cut it off right there and we pretend that this doesn't exist, we pretend that doesn't exist, we now have a one-to-one function because I can draw a line like this and it passes the horizontal line test. Okay. Oops. I passed the horizontal line test. Okay. So this is in fact a one-to-one function. So what we had to do is we had to restrict the domain. We had to restrict the domain, and the domain became from negative pi halves to pi halves, right? That became the domain that we're willing to work with in order to get a one-to-one function for sine of x, okay? So that means that when we take the inverse of this sine x function with this restricted domain, that the inverse of it will also be a function, okay? So that's kind of the price you have to pay to get that, is we had to restrict the domain in order to allow the inverse to also be a function. So then also in this case, the range is from -1 to 1, okay? So I'm going to come over here And I recall something from one of my other classes. Oops, hold on, you guys, real quick. Oh, I lost my notes. Sorry about that. Okay, so we know that this is the domain and range that we need, and you should remember that from your other class, if you want to talk about the inverse, so the inverse of this function, the domain and the range would flip-flop based on the way that we find inverse functions by interchanging the x's and the y's. So that means that over here, the domain would become -1 to 1, right? And then the range would now be restricted to -pi12 to pi halves. Okay, so remember, this is what it means to be an inverse. So we take and flip the domain and the ranges for the inverse from the original function. And then we're going to just draw a quick sketch of this. So a quick sketch of this would look something like this. It's not going to be perfect, but just bear with me. Right, and that's about what I get. So that's what our inverse function will look like. Okay, so that's our arcsine. So that's where it comes from. So when you see them talking in the book about it, that's really all they're doing. Okay, so they're saying that, you know, the inverse function has these new domain and range restrictions, and I'm not going to do it for every single one. You guys, you could do the same thing for cosine, tangent, secant, cosecant, cotangent, so on and so on. That's something you should have hopefully learned previous classes. If you really need help with understanding inverse functions, you can meet with me and we'll talk about it. But what I want to do is I want to develop where a couple of the formulas come from for inverse functions, where the derivative formulas come from. And then we'll talk very briefly about the integration formulas. So I'd like to find, now again, you're going to end up just memorizing these, but I kind of want to show you where it came from. Okay, so I want to find the derivative of y equals sine inverse of x, or arcsine of x. And I want to use implicit differentiation. Okay, so oops.
I can learn to.
So let's see here. It says that we want to find the derivative of y equals sine inverse of x by using implicit. So what we're going to do is we're going to build a formula, and then we're going to, I'm going to give you two formulas that are kind of like your core. There's all 6 for all the trig functions, but I'm going to really focus mostly on this class on 2 particular ones, arcsine and arctangent. You can also do arccosine as well. It'll be in your book if you ever need to find it in the tables. I might even try to post all of them for you, but in the meantime, let's just build one. So what we're going to do is we're going to say that if y equals sine inverse of x, then that implies that x equals sine of y. Remember, there's multiple ways you can think about it. It's trying to say what angle could you plug in there to create this ratio. You could take the sine of both sides, however you want to work with this. So we have x equals sine of y. And basically all I did, you guys, is if you're wondering, if you want to actually see the work, you could just take the sine of both sides, and the sine of the sine inverse is just x, and then the sine of y is just y. Okay, so that's all I did. All right. So or you could just think about it, what's the angle? You could even call x theta at some point if you wanted, but for our purposes, let's just leave it as x. Okay, so we're going to start with x equals sine y, okay, and then we're going to differentiate both sides, okay. So what I'm going to do is I'm going to ddx both sides, okay, so that's going to give me 1 equals the cosine of y, but remember, we're differentiating y with respect to x, so we have to attach a dy dx, or you could even call it y prime. I think y prime will be a little bit cleaner. So I have to attach a y prime because of the chain rule. because just remember, when you're doing implicit differentiation, that inner function, if it's not the same as the original, then we have to differentiate the inner function as well. Okay, so since this is with respect to x, we're going to get that y prime. Now we're going to solve for y prime. Okay, so we're going to have 1 over the cosine of y is equal to y prime. All right, now there's something to remember is pretty much, I don't want to say all the time, but in a lot of trig problems when you're trying to develop ideas, one of the big things you always want to keep in mind is this guy right here. Sine squared theta, or sine squared x. In this case, I guess it's y. Sine squared y plus cosine squared y is equal to 1. Okay, so we know that. Now the thing is we want to find a nice clean derivative that's in terms of x. You know, we want it to be nice. So right now we have y prime equals, but it's y prime equals something in terms of y. So I want to find a way to rewrite this guy. I want to find a way to rewrite cosine of y. Okay, so what I'm going to do over here is I'm going to solve for cosine of y. So this is going to be cosine squared y is equal to 1 minus sine squared y. And then I'm going to square root both sides, right? And then I have cosine of y, we'll take the positive version of it, 1 minus sine squared y. Okay, so I have cosine of y is equal to 1 minus sine squared y. So that means that if I substitute this guy in for cosine of y right here, I will now have 1 over the square root of 1 minus sine squared, sine squared y. Right? But it's still not in terms of x. I still basically am saying this, right? Y prime is equal to 1 over the square root of 1 minus sine squared y. Okay? So we have this, and I need this to be in terms of x. That's what I'm kind of shooting for. But I have to go back to the very beginning. Look way up here. What does it say? And again, this is kind of things that you learn in math as you do more of these problems. Sometimes you go back and check, what do you have to work with? Well, originally it said that x was worth the sine of y. So all along, all this work I was doing, I got cosine of y to be written in terms of sine of y. Now you may not have noticed why that was important, but now look, I have 1 over the square root of 1 minus sine squared of y, but we know that sine of y is worth x. So this really means that 1 over the square root of 1 minus x squared. And this, as it turns out, is our formula for arc sine. Okay, now you can do the exact same thing with tangent. You know, I haven't done the one myself personally with cosine, but arc cosine, but I'm assuming it would work the same. So I'm going to really focus for you guys. I'm going to focus on 2 new formulas. Now in the homework, I believe they'll ask you for, you know, any of them. But when I go to give you the exam, I'm going to try to focus on the ones that I give you here, maybe even cosine, but it's just a formula that you memorize. I don't have that particular one on this page. I'll have to maybe get it out to you guys later. So we have d dx sine inverse. You know what? I don't like this green. Let's use some red. 2 new formulas. Okay, so we have d dx of the sine inverse of x, right? And that's now going to become 1 over the square root of 1 minus x squared, okay? And then we have d dx when we're trying to find the derivative of tan inverse or arctan of x. That's going to be 1 over 1 plus x squared, okay? So this is how we can deal with the inverse formulas. These will be the 2 main ones I focus on for you, okay? So that means, let me do this. That means if we wanted to look at an example, let's say that I gave you something like this. I said y equals the tangent inverse or arctan of 4x cubed, and I ask you to find y prime. Okay, so all you would do is you would say, well, y prime is equal, and we come up here and we see, well, this is the derivative of tan inverse would be this. So I'm going to simply say that it's going to be 1 over 1 plus 4x cubed squared. Notice right here, it says that if there's an x here, whatever it is, you square it. Now, doesn't this seem a little bit almost like suspect? Like in the arctan problem, there's an x, and in this arctan problem, there's a 4x cubed. That's definitely different. So doesn't it feel like you were supposed to be doing this problem, but somebody came along and messed it up and plugged something into there? They plug something into the x. Doesn't that make it a composition of functions? So that means that we have to use the chain rule. Remember, you always use the chain rule when you're dealing with composition of functions. When you're trying to undo the chain rule, you use U substitution. That works with undoing the composition of functions chain rule. So we have to attach, we have to multiply this by the derivative of whatever the inner function is. In this case, the inner function was 4x cubed. So what's that derivative? That would be 12x squared over 1. I'll just write it, you know what? I'll just write it as 12x squared. So then our final answer is y prime is equal to 12x squared all over 1 plus 4x cubed. You know what? We can square that. We know what that is squared. That'll be 16x to the 6th. Okay, so that would be our final answer. This is what, if you were asked this problem on a test question, like as a final result, this would be your final answer. Okay, that's as good a cleanup as I need. All right, hopefully that one's okay, not too big a deal. Let's look at another one. So say we have y equals sine inverse of the square root of x. Well, first of all, I'm going to rewrite this as sine inverse of x to the 1/2, just because I know I'm dealing with derivatives, so I'm going to want exponents. So let's see here, y prime would equal, now we're going to say 1 over the square root, and all I'm doing, you guys, is I'm coming up here and I have this formula memorized, right? I'm going to memorize that formula, 1 over 1 minus x squared. So this would be 1 over 1 minus, but instead of an x, it's an x to the 1/2 squared. Okay, now what do we have to do? Because it wasn't plain old x, we must attach the chain. So the chain rule of this says that we take the power, put it in front, rewrite the inside, reduce the power by 1. Okay, and you're good, right? And the derivative of the inside is 1, so you're good. So then this will become, let's see here, 1 over 2 square roots, oops, that's too big, 2 times the square root of x times 1 minus x. And that would be our answer. Now you could probably clean this up a little bit. I'm not sure how picky the homework is. This is technically a correct answer, but you have 2 square roots that are the same radical, so you might want to just put these guys together. This would become x minus x squared. You know what, I'll leave it just multiplied, x times 1 minus x. Okay, that would probably be what the book is looking for when you're trying to type it into the homework. So this is just, one arcsine and one arctan problem. Oh, I don't know. Let's look at another one. This one's a little bit harder. Geez, this one looks rough. Let's see. Y squared. Oh no, that's a different problem altogether. That's just implicit differentiation. Okay, so let me take a look at one of the ones from another set that I have for you guys. So what if I asked you to find, yeah, let's try this one. Let's try another example. 2x arc, I'll use arc cosine. Oh no, let's not use arc cosine. Let's use 6, yeah, I'll do this one. I didn't write you guys the formula for arc cosine. So I'll say that P of x is equal to 16 arc sine of x over 4, okay? So now we want to find this derivative. So p prime of x is going to be 16 times, now we know the derivative normally would be 1 over the square root of 1 minus x over 4, whatever was in there, squared, right? And then we also have to take the derivative of the inner function. Remember, this is the inner function. This is your g of x, right? Depending on how you were taught. So this is your inner function. So the derivative of that would just be 1/4. Okay, so when we do cleanup, this cancels with this, and we're left with 4 over the square root of 1 minus x squared over 16. Okay, let's see here. Did I do anything wrong there? No, I think that's okay. Yeah, I think that should be good. Yeah, I'm just worried that the homework might try to get, I guess, a little bit fancy with you guys to try to clean this up a little bit better, but I think this is okay. So let's see here. I'd say that's a good enough answer. Let's see if I have another one. Well, I did find my formulas. I might as well write all of them out for you since I have you guys here. So let's just say that, you know, formula 1, d dx of arc sine or sine inverse of u is equal to 1 over the square root of 1 minus u squared du, right? And that's if you, and again, this is basically the chain rule. So if there's ever anything other than plain old x inside there, this is how you can do it. So this is the du that I'm accounting for. You see right here, this is the du that I'm accounting for right here. Okay, that's what this guy is right here. He's accounting for the if it's ever anything other than plain old x. Okay, so we have d dx of arctan. And this, by the way, you guys, you could also use inverse, tangent, or arc, doesn't matter. This would be 1 over 1 plus u squared du, okay? The formula I was using up above right here, they were just if it was plain old x, right? You notice this is plain old x, this is plain old x. So these formulas have plain old x's here. And what's the derivative of x? It would be times 1, so you wouldn't even notice it. So these formulas are a little bit more, I guess, elaborate. They're kind of covering all your bases for you. So this is d dx of arc, let's go with arcsecant third. And this one is a much less common, this one hardly gets used at all, but, and I don't plan on asking you guys this one, but it may just come up in the homework or something like that if a problem sneaks past me and gets in there. So there's that one. 4, let's do d dx of arc cosine of u, and that's going to be -1 over the square root of 1 minus u squared du. Let's do 2 more. We have d dx of arc cotan of u, and that's going to be -1 over 1 plus u squared du. Notice it's very similar to tangent, and notice arc cosine is very similar to arc sine. -1, I keep messing that up. Okay, and then we have one last one, 6 d dx of arc, I think it's cosecant is our last one. Yep, and that's going to be arc cosine of u, and that is going to be -1 over the absolute value of u, square root of u squared minus 1. Okay, du. And again, I haven't, for me personally, I haven't done these in a long time, like trying to derive where they came from. But I'm assuming a lot of similar process that I used, like this one and this one. I don't use these a lot in terms of where I derive them. Now, the ones I will say that you better know inside and out and know when to use them is arcsine and arctan. These are the two big ones. These ones happen all the time. So these are two kind of the big ones, okay? And then this one, the arc cosine, I would say is maybe third most common, but that's pretty much it, okay? And again, if you know arc sine, you probably are gonna know arc cosine. If you know arctan, you're probably gonna know arc cotan because they're the same formula, but off by a negative, okay? So these are formulas that technically you should memorize, but if we're taking the test online, you may end up being able to just use your notes, but you should definitely know how to use them. Okay, let me see if I have a few more practice problems. Let's see here. Okay, so let me see if I can come up with this one. Consider the function. Let's see here. Sure, I guess we'll try this one. I don't have this one worked out, but let's give it a shot. So suppose we have x squared plus x tan or arc tangent tan inverse of y equals y minus 1. Okay, and you have it at the point negative pi over 4 comma 1. Okay, so I'm going to ask you, supposedly, find the slope. This might be one in the homework as well. I might put this one in the homework. Find the slope of the tangent line to the function at the given point. So more than likely, I hope you guys can recognize right now that this is going to be some kind of what's it called, implicit differentiation, because we're going to be taking the derivative with respect to x. We're going to ddx everything, and that means that anything that has a y involved is going to be a dy dx floating around somewhere, because we have to use the chain rule on it. So let's write this problem out. Let's find the derivative. So what I'm going to do is I am going to ddx both sides. Remember that, just taking the derivative with respect to x. Okay, and let's see what we get. So you guys all know that when I ask you to find the slope of the tangent line, what I'm really saying is find the derivative and then evaluate the derivative at the given point, and that will find the instantaneous rate of change or the slope of the tangent line at that given location. Okay, so when I take the derivative of x squared, I get 2x. When I take the derivative of x tan inverse y, I have to remember that this is a product rule. So this is going to become plus tan inverse of y. So I took the derivative of x, which is 1, multiplied that. This is a little too close together. Plus 1 times tan inverse of y plus x, rewrite the one that I did not take the derivative of last time, and then take the derivative of tan inverse of y. But we know that the derivative of tan inverse is 1 over 1 plus whatever was in the angle, or whatever was inside the arctan's argument. You square it, so y squared. But I have to attach a dy dx, or a y prime. Let's call it y prime, just so it's easier to work with. Okay, and that's going to equal y prime over here. The derivative of y is y prime with respect to x, right? And then the derivative of 1 is 0. So that's my function, and they want me to find the slope of the tangent line, so that means I have to, I guess you could do it two ways. You could plug your values in right now and solve for y prime, or some people, including myself, I normally like to get y prime by itself. So that means I'm going to have to isolate the y prime. So that means I'm going to have 2x plus tan inverse y, and then I'm going to subtract this whole chunk over to the other side. So this will become y prime minus x over 1 plus y squared, y prime. Okay, so I subtracted this whole chunk over to the other side. Now I'm going to factor out the y primes. Right, so now I have y prime isolated. So now I can divide both sides by 1 minus x over 1 plus y squared. Divide this by 1 minus x over 1 plus y squared. So this should cancel this and become 1. So let's rewrite and see what we got. So this will become 2x plus tan inverse of y divided by 1 minus x over 1 plus y squared, and all of that should equal y prime, or dy dx. Okay, Now what we can do is we can evaluate this. So I'm going to do y prime, and I'm going to evaluate it at the point. Depending on the notation, I'm going to use negative pi over 4, comma 1. Some people choose to use like a little bar like that and then put it at the bottom. It's just a preference. So then we have 2x, oops, not x, I'm sorry. 2 times negative pi over 4 plus tan inverse of 1 all over 1 minus negative pi over 4 divided by 1 plus 1 squared. Okay, so let's see what all that cleans up to be. Well, we know tan inverse of 1 is going to be pi over 4 because it's basically saying what angle would give you a tangent of theta equal to 1. So we know that that's the angle pi over 4. Okay, excuse me one second. Sorry about that. So this is going to be negative pi over 2 because these cancel, right? And then this is going to be plus pi over 4 divided by, I think that bottom should clean up to 1 plus, what is that, pi over 8 once you clean it up. Yeah, because it's going to be pi over 4 divided by 2, which is the same as multiplying by 1/2, which becomes that. So when all is said and done, I think we end up getting negative 2 pi over 8 plus pi. Okay, so this is, and I believe they asked us to find the slope of the tangent line. So here we go. Here's our slope. A lot of work to do it, but we kind of showed that we know how to work with arctan. We know how to work with other problems. It's really not a big deal, but I am incorporating a new formula. And I think if you're kind of rusty on your implicit differentiation, this is kind of a good follow-up. Again, I don't think this is an easy problem. This is definitely a harder slope of the tangent line problem, implicit differentiation problem, but it is doable. You just have to make sure you understand how to do implicit differentiation. If you're having trouble with this, log on to the meeting the next day and we'll talk about it, okay? I can kind of maybe try to find another one or discuss where I went with each different problem. Okay. I'm not going to do a whole bunch of integration with these. There'll be two main ones that I'm going to focus on. And actually some of the trig substitution we do, you'll notice is maybe derive some of this or build some of this. So if you ever run into this, a squared minus u squared du, when you run into this as an integral, you can now say that this is sine inverse or arc sine of u over a plus c, okay? And then you have this other one over here where we can say the integral of 1 over a squared plus u squared du is equal to 1 over a tan inverse of u over a plus c. So these are the two main integral formulas that I'll ask you to do. There's other ones that come from secant and stuff that when we do trig substitution, you'll kind of recognize these look awfully familiar. But basically your job in these problems is to identify what a is and identify what u is. When you have a square root and you're subtracting a constant minus a variable, then it's a sine, an arc sine. When you have no square root and it's addition of two perfect squares, then you know that it's an arctan. And I guess they don't even really have to be perfect squares, but normally that's what a lot of the time you end up running into. So these will be two formulas that you guys can work on. Or, I would definitely start making like maybe note cards of all the formulas I'm giving you so you have them as like quick reference, okay? So what I could do is I could say, I could ask you to evaluate this integral 2 over the square root of 16 minus 9x squared dx, right? So if you think about this, your job is kind of to identify what a is and what u is. So in this case, I know a is worth 4, and I know u is worth 3x, right? Because it's something squared. So I have to be able to write a squared minus u squared. So that means technically I could write this, and I could even pull the 2 out. This is 1 over the square root of 4 squared minus 3x squared dx, right? So I basically rewrote it so it's kind of nice, okay? Now, the thing is whatever I name my u, it's just like u substitution. So I'm going to say that u is worth 3x. So then du is worth 3 dx. And then we divide by 3. So you cannot forget your u substitution with this technique because you'll always be off by a coefficient, some kind of constant that you'll forget to have divided by or multiplied by. Okay, so now when I rewrite this, this becomes 2 times the integral of, let's see here, 1 over the square root of 4 squared minus u squared times 1/3 du. I'm going to move the 1/3 to the front. So this will become 2/3 integral of 1 over the square root of 4 squared minus u squared du. Okay, so now we have it in the correct format. We have it in the format where it's a squared minus u squared. And that's what they said we need. Right here, they said we need that. So now I can just say that this is 2/3 sine inverse of u over a. Okay, so u over a, but in this case, a is 4 plus c. However, what's u? We know that u is actually 3x, so this becomes 3x over 4 plus c. So again, not the easiest problem in the world, but definitely doable if you think about where you're trying to end up. You need to end up to look like this or to look like this. So you need to rewrite the problem to look like that. So if you can rewrite it like that, then you can use the formulas provided. So that's kind of your goal with these, okay? Let me see here. I can give you kind of a sneaky one. This one's a little bit sneakier. So let's say we have the integral of e to the x over 4 plus e to the 2x dx. Let me see if I can figure out how to do this one real quick. This is a little bit sneakier one. Oh, I guess it'll be okay because of u. Okay, so what we're going to do is we're going to kind of identify this for what it really is, right? In this case, isn't it really e to the x over 4 plus e to the x quantity squared, like that, dx? So this looks an awful lot like this guy, right? It looks an awful lot like that guy. So I now can declare my u to be e to the x du is worth e to the x dx, right? The easiest derivative ever of e to the x is e to the x. So now we have the integral of du, or I guess we could do it this way. We could say 1 over, what is that, 2 squared plus u squared du, because remember, this e to the x dx is worth a du, right? So I replace this whole chunk of information, I replace that with du. That's where this du came from right here, okay? So this doesn't look so bad. Now I go up to my formula and I say, do I have it in this format? Yes, I do. So then I do 1 over a. So this is going to become 1 over 2, because a is 2, times the tan inverse of u over a, right? Let's see up here. Oh no, I'm sorry. Yeah, u over a. So then u is actually what? E to the x? Oh, I'll write it as u over a. U over 2 plus c. But then you guys know that we can't leave it in terms of u. So this will become e to the x over 2 plus c. And that will be it. So 1/2 arctan of e to the x over 2 plus c. So these are kind of the main integration techniques that I'll focus on. I'm not going to do all of them. You know, it's that we got some more coming. There's some more stuff for us to do. I'm not going to go too heavy into this. I think this video was already longer than I wanted it to be. And I'm not going to give you per se like exact test questions, but every once in a while a problem's going to come up that uses, you know, inverse trig, and you just have to know what it's talking about, right? It's talking about what would the angle need to be that would have created this ratio, okay? So normally with trig, they give you the angle and they want to know the ratio. But with arcsine, arctan, and inverse trig, they give you the ratio and they want to know what angle would have created that. So you're kind of thinking backwards, okay? So that's going to do it for this video. I'm going to post this on Canvas for you. Thanks for watching, and I'll see you in the next meeting.